visualization. And one thing I want to make clear is that you can't go, I mean, we plotted up the raw data. I mean, you got to do that. You got to take a look at it. And in this case, we made this discovery, which surprised us. It didn't dawn on us. We figured it would come out of the gateway just perfect. I mean, not the case. But actually, visualization is something which you really can't get too. I mean, you can learn a lot of things, but you really need to keep it up as you go through the analysis. It needs to accompany the whole analysis, because if you just look at raw data without doing something else with it and then visualizing the something else, then you're not likely to get too far. So the process of using numeric methods of statistics and machine learning is also a part of the process of visualization, because you'll sort of fit something. You'll do something and then look at the output of that something, but that something gets visualized, and that process is extremely important. So the visualization is something that just goes along with everything you do as you go from the beginning of the analysis all the way down to the end. All right, let's talk about the jitter. Let's get back to that. So we're in a situation where we thought at first that it was going to be mostly about what was the sending gateway and what's the traffic rate on the measured link. Those are going to be the two factors. And suddenly we find there's this other source of variation. And so, and that's the cycle of 9. So what we did was the following. We're in a case of factor response analysis. What we have is we have these jitter values. That we have three factors. We have the source gateway, and we have the traffic rate on the link. But now we have this other thing, which is sort of it's an index I. If we're looking, in each interval, there's jitter 1, there's jitter 2, there's jitter 3. There is an index here, and now that becomes in a sense, a variable itself on which the values of jitter are going to depend. And that becomes, in a sense, and that's it's a within subset variable, really. That's not a between. These are between subset variables, but this one it's a factor in explaining what's going on, but it's a within subset variable. All right, so what we did was to fit a cyclic parametric function of I to each j sub I for each transmission interval. And then we used bi-square fitting because also in doing some other exploratory plots, it looked like there were a number of outliers. It wasn't too bad, but we figured, what the heck? Just use the bi-square. We use it because we can, and it's a bit safer. And remember that you might say, well, gee, I mean, you have so much data. I mean, are the outliers going to have an effect on with that much data? Remember that actually, in each instance where we apply this, we don't have a huge amount of data. I mean, the intervals, each interval itself is most of them anyway, are small data sets. So it's like a very, very large analysis of a whole lot of data sets. However, we didn't do it with somewhere. I guess I'm saying this a little bit late here, but actually what happened was that we didn't take all 14 million intervals. Because for us to remember, what we're trying to do is to understand what's going on here. So if we have intervals that are very short, then it's going to be hard to get a good estimate. I mean, if they get really short, if it gets, well, obviously, if there's less than 9 values, we're in real trouble. But you want to have several replications, or a number of replications of the cycle, if you expect to be able to fairly get a pretty good estimate of the underlying cycle behavior. So what we said was, well, okay, we want at least 20 cycles. So we only did this analysis I'm about to tell you about on intervals that had at least 20 cycles, which is 180 jitter values. And that took us from 14 million down to 14.1 million down to 3.6 million intervals. But when we started, we had 1.23 billion packets. With these intervals that have 180 or more, we're down to 885 million. So obviously, you know, a large fraction of the packets or the jitter values are contained within the larger intervals. Okay, so the idea is this: we're gonna fit a cyclic function to the jitter, and then we're going to subtract the bi-square fits, and get the residuals q sub I. So we get some sort of cyclic function that's been fitted, and it's exactly cyclical. We subtract it away, and we say, okay, that cycle is what's coming from the gateway, and the rest of it is the network jitter, the network queuing jitter. Okay, so we'll use Q to note the residuals. And then we'll model Q sub I as a function of the traffic rate for each source gateway separately. And that network jitter, now that thing that now that we'll call network jitter, we expect that to depend on the source gateway and the traffic rate on the measured link. And furthermore, we don't actually know the internet distance of these source gateways in the sense of how many hops are there. So we weren't able to get that information. But we know air distance, and while you know the number of hops is obviously related to the air distance, so we expect to see Buenos Aires to have more jitter than some close place in the U.S. So there's the variation in the data are the gateway induced jitter, the queuing jitter, and then noise. Noise coming from the fact that we can't capture the queuing jitter terribly accurately. The best we can do is just get it, well, we can get it from, the source gateway being a variable and the traffic rate on the link being a variable that's predictive. But there's a lot of other noise in this, which is the changing traffic rates on other hops along the route. And we'll do a stepwise fitting. So what we did was to fit cosinusoids. So these are a constant term plus, which is a cosine that's DC cosine if you're in electrical engineering, right? So it's a constant plus four sines and 4 cosines. And so in other words, that would reproduce exactly, if you had just 9 points, this will reproduce. It's a decomposition of 9 points into whatever cyclic. So this will accommodate any cyclic pattern of length 9. Okay, so the model is the jitter. This is within one interval. The jitter is this function of sines and cosines with unknown coefficients. The alphas and the betas are unknown. That's what gets estimated. And the phi is the error term. All right, so we take 180 or more values. Now, we do have a picture. The log base 2 of 180 is 7.49. I think the picture is here. Remember, this is the plot, we saw this earlier, that shows the log number of jitter values in the 14 million transmission intervals, and 7.4. This is the quantile plot. Remember, as we go up here, where this value here, say at 0.5, is a quantile of order 0.5, which means that 50% of the data are less than or equal to that. So that's the median, and here 0.75, that's the upper quartile, and so forth. So if we look at 7.5, that's up here somewhere. So we're getting about the top 20% of the intervals in this regression. I mean, the largest 20%, rather. OK. So we fitted the 3.6 million robust regression to these intervals, and computed residuals. Or actually, no, that's just the fit itself. I have a time here of 750. That doesn't include the computing the residuals, or does it? I've forgotten. Well, it doesn't matter. Most of the time it's taken up in the... That's the whole... No, it's the whole thing. Yeah, it's the whole thing. OK, so it's the fitting, it's the estimation of these 3.6 million, well, the coefficients. So it's actually 9 times 3.6 million estimates. But also the bi-square is iterating to do its robustness thing. So there are 3 iterations to that. So we get the estimates, and we get the fitted values of those estimates. So those are, you know, the predicted values of the cycle. And then we subtract those from we subtract the fitted values from the original observations, and that gives us the network jitter. OK? Any questions about this process? Or?
I was wondering if you looked for any other frequencies, like do an FFT or something like that. I mean, there's clearly a 9 cycle, but what about some higher frequencies?
Actually, that's yeah, interesting question. We didn't do that. We didn't take the power, look for other frequencies, do an FFT with Fourier transform with the jitter values themselves. But not discussed here at all, and not part of our presentation, is that we actually took the multiplex traffic and did a power spectrum analysis of that. And we could see this cycle of 9 in the multiplex data. So it's powerful enough that it comes out rather clearly as peaks in the power spectrum of the multiplex traffic, so we can see that. But we didn't see anything else beyond, well, the usual kind of thing you see in network data like this. So that was the only thing that popped out. So if it was something else, it wasn't powerful enough to break through into the multiplex traffic. But still, there could have been other things that or more delicate that just can't manifest themselves in the multiplex traffic, sort of get washed out. So, interesting question, though. Yeah, maybe we should have done that. OK, so now the question is, you might say, all right, well, I mean, how much of this of the jitter is being accounted for by this cycle at this particular time? So what we're going to do is we're going to look at 3 things here. We're going to look at the absolute jitter. I mean, what really matters, and we've been dealing with the cycle, because there's a cycle there, and it's plus and minus. The jitter is positive and negative. And more or less, there's a certain symmetry to this, because if one packet, let's say just you got 3 consecutive packets, and the one in the middle arrives somewhat late, then one of its neighbors has a positive jitter, and the other neighbor has a negative jitter, whose absolute value is exactly the same. Okay? So there's a certain, if you're looking at just the jitter itself, there's a kind of, there's a very strong correlation in this jitter process. So in any case, but what really matters is the magnitude of the jitter. So it's really absolute values. So here, at this point, what we're going to do is, having observed the cycle and sort of fitted it, now what we're going to do is, when we look at components, we're not going to actually look at positive, negative. We're just going to take the absolute value of those numbers. So here's positive, the absolute values of jitter, the fits, the cyclic fit, the values of the cycle curve fitted to the data, and then the residuals. I'm going to make a plot, and what we're going to do is, you'll see less than sign is going to be the median, a circle is going to be the upper quartile, a plus is going to be the 0.9 quantile, and the x is going to be the 0.99 quantile. So here's the first plot. I hope you can see it. Oops, it's getting cut. Nork, is that a, no, that's not even all there. That's interesting. Is it over here? No. Interesting. I got it all? I think so, yes. Okay. All right. All right, so here we are. Actually, now you're getting to see all the sites. So what have we got here? We've got in the left panel, we've got the total jitter. So that's the original stuff, you know, as measured on the link. And so remember, it's the median, the upper quartile, the 0.9 quantile, and the 0.99 quantile. And so as you look at this, you get a sense of the magnitude according to the different gateways. And the gateways have been ordered by their distance from the measured link. So notice there's Buenos Aires up at the top, and not too surprisingly, if you look at, you know, especially the upper 99% point, you'll see that Buenos Aires is got the largest 0.99 quantile, and in fact, just in general with the raw jitter, as we come up here, there's a little bit of an increase in the quantiles, but it's really the larger values that we're seeing, you know, the big increase in as we go up to as we go up to places further away. But and here's the residual jitter. So this is the network jitter. So you can see that actually that a lot of obviously that's network related. This increase as with distance. But the interesting thing is the cycles. Actually, well, it's what you would expect if the hypothesis is correct, and it almost has to be because there's really nothing else it can be. Really, you in fact would expect to see about the same magnitude. You expect this equipment, the equipment, you know, since same model, same supplier, you expect the equipment to be operating in about the same way in terms of an overall magnitude. Okay, and you get to see that. I mean, actually down here, the median, you might say, well, the median is jumping all over the place, but remember, we do have a lot of, we're getting things close to zero. There's a kind of discreteness where, you know, you actually get a lot of zero jitters, you know, the median doesn't do very well for discrete data. So the median's sort of jumping around because it's not a particularly effective statistic when there's an atom, you know, in the data. So anyway, all right. So there's a look at what the results are of this regression and how much of variability it's explaining in the regression. So there is obviously this is a pretty major, you know, it's a major amount of the variation in the data, because when we look over here at the residuals, we see a fairly big reduction in these quantiles compared to what they are over here. As a matter of fact, you can see that in this plot here, where we've actually taken for each case here, each source gateway, we take these 4 values and plot them against these 4 values here, and you see that, so the absolute total jitter is on the vertical axis, and the absolute network jitter is on the horizontal axis, and you can see that we're getting a significant increase across almost all of the sites. Okay? All right. So now we want to know about the network jitter, and what we're going to do is study the network jitter. We take those residuals and take their absolute values now. We're going to be studying now the absolute values, and we're going to study them as a function of source gateway and transmission rate on the measured link. Okay, so the magnitude of the network jitter is the salient aspect of jitter. So Q sub I bar, Q sub I, absolute Q sub I was modeled as a function of source gateway and traffic rate. And in fact, now the transmission interval of which Q sub I was a part plays no role in the analysis. Now that we've gotten rid of this effect, which has to do with the index and where it occurred, now it doesn't matter sort of when it occurred in its transmission interval, except or with respect to the other values. Now what's going to matter now is what the traffic rate is on the link and what the source gateway is. Okay, so the factors are source gateway and traffic rate, and we've lost the transmission intervals. So the source gateway becomes a conditioning variable, which divides these jitter values into 27 subsets. So, and of course, associated with every jitter value is an arrival time of the first packet. So we're still going to retain that because we have to know when it occurred, so we know, what was the traffic rate at the moment of that jitter. Now we have to get that traffic rate, and what we did was the following. And by the way, this is the traffic rate. We have to now use the traffic rate of all the packets. So we have to go back to let's say the basis division. This is the raw data. You have to, if we're going to compute a packet rate on the link, we have to use each and every packet that appeared. So that's back to the basis division. You could put it that way. The way it was actually computed, at least this is my understanding, we actually read the HDFS arrival times in the text files into R and computed the rate. Get all those arrival times, bring them all in, and compute the times. Because the arrival times are all ordered from smallest to largest in the multiplex data. So you say, oh, that's what I really want. I want to get at those numbers because they're ordered, and now it's an easy calculation. All right, now, although what I wonder is whether or not we could have gone back to the basis division where they're now separated.
I did.
You did? What happened?
That's the observation I made, yeah. So the point is that we went back to reading the text files in the first iteration of this research, and that's just kind of against the principle of, read the data in once and convert it into a data frame.
Right.
So you can do it from the basis division, and I wrote code to do that.
So how, did you time it?
I didn't time it. This isn't an... Okay. I didn't time it.
Yeah, excuse me. You don't mind if we work in the middle of your class, do you? I mean...
Okay, so the question is, how much faster does it run? And so in one version, we're reading text files, and we're calculating the rates of the packets are arriving. And then in another version, we've already read the text file, we're working with the data frame, and we're calculating how fast packets are arriving. And the answer was much faster, but I didn't record the numbers. So,
Okay, so it is faster. Wait, I'm sorry. It's faster. It's faster to go to the basis division.
Oh, of course.
Yeah. That's what I. Okay. All right. Well, of course. See, we've already developed principles now. We know what's going on to some extent. Well, we already knew that. I mean, the reads into R are just slow. I mean, that's the way it goes. So, I mean, you don't have to actually do big data to know that. So, yeah. Okay. All right. Good. Well, good, because that's sort of intuitively, that's sort of what we would expect. However, there is another thing here, though, actually, is that there are analyses to be done on the multiplex traffic that are of use. So you might say in a bigger analysis, those things are going to get read in for the looking at the time sequences. Looking at the time characteristics, the time series characteristics of the multiplex traffic. So there would be plenty of reason just to gut those things into R as part of another kind of analysis. And had that been done, then of course, and they were sitting there as objects, then it becomes really fast to be able to do it using those because they're ordered. So, okay, good. All right, well then, I take it back. We did it the other way. So are we will, well, we actually didn't really, historically, we'll say this is the way to do it. Okay, but what we actually did, and I even think maybe we probably should have picked a smaller interval, but we said what we're going to do is we're going to find out what the traffic rate is in 30, I mean, you have to pick some, if you want to say, oh, I want to talk about a rate, you need some way to do that. You've got to sort of look at, you say, all right, well, this occurred at this time. What's the rate at this time? Well, what does that mean, by the way? Actually, this is a big issue in sort of network engineering. What do I mean by the traffic rate right now? Do I aggregate over, a second, a minute, an hour, 2 years? I mean, what's the relevant time interval? So, well, we picked 30 seconds, but we've had the benefit of seeing some of the queuing that goes on through simulations. So that's probably better to be a smaller number. But anyway, it is what it is here. So you take the counts in every 30-second interval across the whole data set, and then you say, okay, here's my jitter value, here's the time it occurred, I will find out what interval it's in, and then I'll take that 30-second interval as being the rate associated. That's the R sub I, which is associated in this with this particular J, with the J sub I. Okay, so we actually have now, what do we have as a result of all this? We have 3 within subset variables, the absolute jitter, the arrival time of the jitter, and the rate on the measured link at that time. And we have now a new division. This is a second jitter division where, or the beginning of a second jitter division, which we call source gateway and replicate division. It's divided up by source gateway. So we have 27 subsets of these 3 variables. Okay? But here is a display of the counts, the number of jitter values in each of these subsets. So it's log base 2 on the x-axis, log base 2 number of jitter values, or 10, sorry, log base 10 number of jitter values. So we're going from something that's on the order of about 30,000 up to something that is let's see. So is that the right? Oh yeah, that's right. Yeah. So we're seeing something that's up to on the order of about 500 million. In fact, I have the exact numbers here. I think yes, 429 million. Sorry. Sorry, yeah, the numbers at each site. Yeah, sorry, the billion is the total. So we have something which is we go from about 30,000 up to 429 million observations. So so the problem here is that we want to take each one of these subsets and start applying things like Loess and parametric regression and any kind of function, any kind of function or response factor modeling technique or analysis method that's available in R, we want to be able to use it. But 430 million values are just going to be too many. So what we need to do is we need to break up the subsets, most of them. I mean, the one that has 30,000 we're OK. But we need to break these subsets up further. We've done the conditioning that we can. And now what we've got is replicates. Or what we will have is replicates. So the problem is the subsets are too large. There's no longer any, shall we say, there's no longer any conditioning variables. Anything we can say, well, you know what, it actually is depending on something else, and so let's break up according to something else, and that will make it smaller. We just don't have that now. By the way, this has happened to data as it originally comes in, I suppose, although I'd be a little surprised if it wasn't something that you couldn't break the data up with. But ultimately, you get down to this case where I still have too many values, and I can't compute with it. So what am I going to do? Now we're just doing simple replicates. No conditioning variables remain. And so what we'll be doing is computing a level 2 division, dividing the data further. We think of the conditioning variables as the subsets you get as a level 1 subsetting. And now we need level 2 subsets in which we go in. And the level 2 subsets inside of each level 1 subset, those things will just be simple replicates. In the sense that you can think of those subsets as being, different experiments. I ran some experiments under the same conditions, and I got data from this experiment, data from this experiment, data from this experiment. And I have no variables that measure the differences between the experiments because they were all the same so far as the information I have. So here's now where we depart from what you would do with small data. With small data, you say, OK, I broke it up according to conditioning variables. I will do my analyses. That's gives me very penetrating results or insight into the data. And you do that as an analytic best practice. And we've taken that to the, we've taken that to the large complex data setting. And in fact, it helps with the computation, but it hasn't helped enough. So we have to do something in addition. So we do these simple replicates purely for computational reasons. So what that means is you're going to design the size of each of these replicate subsets so that you're able to compute with it. So you can readily analyze it and look at it within R. And also, actually, you're paying some attention to Hadoop and how Hadoop performs. And basically, what you'd like is for things to be on the smaller side for a variety of reasons, yeah.
So can you elaborate on that? Because, 400 million is not very large in terms of memory. So, supposing each thing is like a double or something like that, that's not very big. So I'm curious what the problem is.
The problem is that the analysis routines that we're going to be invoking aren't going to, we're not going to be able to take any routine whatsoever in R and apply it in principle, and in particular the things that we wanted to apply in this case. It's not a question of memory. It actually can be a question of memory because you might, it's not just about fitting the things in memory. If you use R, remember, there are just all sorts of copies of things being made. So it's to take even, I mean, this is a simple case too. For example, we're going to be using Loess shortly. To take Loess and then use it on 429 million values, it's going to sit there for quite some time. And also, we want to be able to plot things up. So while we can, make big plots, shall we say, with lots of points on them, 429 million is just too many. So also, you don't, this Hadoop framework makes you want to create smaller jobs rather than larger. There are two reasons. One is just simply the efficiency for you as an individual. So you'd rather have them all sort of, you want to get them down to a moderate size, let's put it that way. You also want them to actually have commensurate size. I'm going to quit in just a second. You want them to have commensurate size. But the other thing is, you have to, actually I'm going to talk about this later, but we'll talk about this tomorrow, but you also want these things to be a shared environment. So you'd prefer to have a whole lot of little jobs going on the part of every individual, because it's much easier now to run a community cluster and share when each individual is running a whole lot of little jobs that when they complete, you can give them to somebody else so they can get their fair share. So there's a whole lot of things going on, not to mention just simply the statistics part of it, using R to carry out the analyses. So you've got to get them down smaller than, for most things I would say probably more than, it depends. Some things you can still do with the 429 million values, that's okay. But to have the scope that's needed, and in this particular case, as you'll see as we go through analysis, we certainly would have gotten ourselves into trouble with, sizes that big. So, and we have to plot them. So, okay, I'll quit there, and then we'll resume tomorrow.
Thank you so much.
Okay.